So my presentation is about KVM storage performance, comparison between different modes of in the KVM. My name is Venko, solution architect at Storepool, and I have a very difficult task to fit 40 slides in 25 minutes. So what is this presentation about? It's basically a very complex answer to one simple question. Which option should I choose when I create my virtual machine? Usually you have an option to create a storage driver, enable iothreads, and so on. And this presentation should give you an answer which is the best. And because I'm not sure I'll be able to get to the end, to the last slide on time, here is the last slide. This is what you should choose. Well, seriously, it's not so simple. It's not the full story. And in this presentation, we will see many different options and many numbers and why these are important. So let's first start with this. The storage path in the QEMU in KVM virtual machines is very complex. I will not go through this. It starts from the guest kernel, going through the QEMU process, and then processed by the host kernel and the actual host devices. And in this presentation, we will deal only with this part of the entire stack. So there are a lot of other stuff that are not covered here. If we have to cover, we will need a whole day. So in this presentation, we will see the different async IO backends that are supported by QEMU and by Linux kernel. So there are basically three. Linux kernel supports three main interfaces for storage: synchronous, standard synchronous interface that in QEMU is using threads to deal with it. That's why it's called threads. Linux native asynchronous IO, it's called native in QEMU and libvirt, and the latest one, iothread. Actually, it's already 6-7 years old, but you'll see this. Also, we'll see what's the difference when you run the I/O processing in the dedicated iothread versus the main thread of the QEMU process. We will see the difference between different virtual devices, VirtuoBlock and VirtuoSCSI. What is the impact of running more than one iothreads? And what's the impact of running virtual machines with huge pages versus standard Linux 4K pages. For different configuration, we'll measure and we'll see the results for read and write latency, maximum IOPS that can be reached by a single virtual device, not the hypervisor or the virtual machine, the single device. How latency depends on the load. We'll see the application performance simulated through pgbench and rsync, and what's the CPU usage consumed by the storage operations. So we will not talk today and will not see about different performance of different hardware. So we will not compare Intel versus AMD, Samsung versus Micron, and so on. We will not compare different storage types, whether local or NFS or whatever is better and how they perform. We will not compare different image formats, storage technologies. We will not talk about any storage vendors. We will not talk about different hypervisors. It's KVM only. We will not discuss different kernel and QEMU versions. And most important, we will not cover many other available technologies in Linux and KVM, like vhost SCSI, vhost user, and so on. So if you hope to see something like this, I'm sorry, maybe next time we'll make a talk about this. Okay, so the test setup, I'll skip this. There will be linked at the end. You can see the details. The most important thing, the host is latest Debian 6.12 kernel with the latest QEMU. Same for the guest, Debian 13 with 6.12 kernel. Virtual machine, the important part is, okay, I have a mouse, a pointer here. So we have a direct block device to the local NVMe. So virtual device is directly mapped to a local NVMe, and different tests change mainly these parameters in blue. Okay, so let's go to the result because we have a lot of results. First, we will compare the different QEMU storage backends. As I said, there are three different backends, threads, Linux native IO, and IO-Ring. And Linux native IO is measured in two different configurations. When it's processed, IO operations are processed in the main QEMU emulator thread, and when a dedicated IO thread is used. So be ready for a lot of such diagrams. So here we compare all these three, and here we compare the latency. The latency is measured with a random read on the left, random write on the right. Block size 4K, queue depth of 1, so standard latency test, measuring different configuration and compare them with the same test executed directly on the same NVMe device from the host. So basically, this is the processing time of the whole virtualization stack, not only the QEMU, but the main contributor is QEMU here. So we can see each backend, how much latency it adds to processing IO operations. What is important here, threads is the slowest one, as you can see in many other tests. Native and IO-Ring are very close, especially for write latency. Native without IO thread running in the main emulator thread is much worse, and you should avoid it. And basically, there are other reasons why you don't want to run this. So basically, in all tests, we will compare threads native with IO thread and IO-Ring. IO-Ring is also with IO thread, dedicated IO thread. Okay, I'll skip this. The same data, just different presentation. So the maximum IOPS you can process from on a single virtual device. Again, threads is 3 times lower performance compared to native and IO-Ring. And again, native and IO-Ring are very similar, about 3 times better than threads. So please note the actual numbers. Even threads is very low on the diagram. It's more than 50,000 IOPS. You have a very few applications that would require more than 50,000 IOPS on a single virtual device. So throughput. Throughput is measured with large block size, 16 megabytes. And as you can see here, all the technologies give exactly the same results as the results from the host. This is because the bottleneck is the actual NVMe device. In this case, it's actually a write array of 7 NVMe devices to get most possible throughput. So I managed to get 64 gigabytes per second, and any technology is capable enough to cover this. So we will not talk anymore about throughput because even the slowest technology is completely adequate to run any throughput you can get. The difference comes in CPU usage. So here is measurement of how much CPU is used by the storage stack, not by the virtual CPUs, but only consumed by the emulator and the IO thread to process 1000 IOPS. And you can see there is about 3 times difference between threads and native and IO-Ring. Let me check. Okay, great. CPU usage for throughput tests, where we have a small number of, relatively small number of IOPS, but large, a lot of traffic. So this is for 1 gigabyte per second. The difference is not so big as with many IOPS and smaller block size, but still significant difference, about 2 times the CPU consumption is higher for threads. So this is one of the most important diagrams in this presentation. Let me try to explain this. So on the x-axis is load in number of IOPS generated on the virtual device. and on the y-axis is the latency of the time need to complete the operations. So the colors are the same. And this diagram shows how actually in real workload the latency will behave. Obviously at low load latency is lower, and when we get to this part here, so something more than 100,000 IOPS, the latency start increasing even for native and IOU ring. This shows us where are the limits of these technologies, of these drivers. So what you can see, native and IOU ring are almost the same, especially at lower load. So this is zoom in of the same diagram. Below 100,000 IOPS, they are in practice equivalent. For any application, it will not make any difference whether it works with a virtual machine using native or IOU ring backend for the QEMU process. Of course, without iothread and for threads, the difference is huge. So yeah. The first application-like test is rsync to see what's this synthetics benchmark impacts the actual applications. So this is rsync time, syncing about 3 million files for a total of 46 gigabytes on X4 file system. And this is time it takes for each technology to complete this job. So you can see, as expected, threads is the slowest, given taking the most time, and native and IOU ring are very close. In this case, native is even a little bit better than IOU ring, but the difference is not so big as we saw in the synthetic test. So synthetic tests show huge difference. When we went to more realistic workload, the difference is not so big. The other application-based test is pgbench. So who knows what pgbench is? Okay, pgbench is a benchmark for PostgreSQL database. It runs a standard set of tests. And this diagram actually collects a lot of data points. The similar way on the x-axis is a different number of transactions per second, different load on the system. And on the y-axis is the transaction time. So we can see here, again, threads is the lowest performance with the least maximum IOPS, just a little bit above 8,000 transactions per second, sorry, not IOPS, and the highest latency compared to the rest. And native and IOU ring are almost the same all the time. So the difference is within the error of measurement. So again, if you run a very application that's very heavy on transactions, they will not see any difference between native and IOU ring. However, even if you run the lowest performance with threads, at a moderate load at about a few thousand transactions per second, the latency would not be, or the transaction time is not so, the difference is not so huge. Yeah, but okay, so the next parameter we study here is using more than one iothread. So multiple iothreads are supported on a single device, is supported by the latest kernels and the latest QEMU, this QEMU 10 that supports this. First, don't confuse this with the number of queues. Number of queues in the virtual queues in the driver, in the virtual device driver, is completely different. It's always recommended to match the number of virtual CPUs. This is how many threads the QEMU process uses when it talks to the host kernel processing the IO requests. So usually it's only one, but you can set multiple queues, and multiple queues can be used by a single not queue, sorry, multiple IO threads can be used by a single virtual device. So threads natively is multi-threaded because this is how it's made. It creates a lot of threads working in parallel. But in this comparison, we will compare the number of physical CPU cores allocated for threads driver. And native IO and ioRync, they can run in the main queue event loop, in a dedicated IO thread or multiple IO threads. So we will compare this. So on the left side is the result for threads. This is again the latency of the IO operation. Blue is read, red is write, and on the X is different measurements with different number of IO threads. As expected, there is no, for every technology, there is no huge difference on the latency, whether you use one thread or the requests are distributed across multiple threads, because here we have queue depth of 1. Still, one thread has a little bit lower performance. It's most visible here in ioRync, this difference here. Lower latency, sorry. Better performance, lower latency. Thank you, Bojan. So the story is completely different when we're talking about maximum number of IOPS a single virtual device can handle. As we saw, a single device usually can handle about 200,000 IOPS, and with adding more IO threads, we can scale this number. So we can see that with 8 threads, we can basically triple the number of IOPS that a single virtual device can handle. And this is true for all the technologies. Important part is how much, okay, before going to this, let's see how this impacts the transactional workload, again with pgbench. So we are measuring the same thing. The solid lines are different technologies, different colors are the technologies, and solid line is one IO thread, dot lines are 2, 4, and 8 threads. Contrary to the expectation, the best performance, maximum transactions and lower transaction time is achieved with a single IO thread. I don't have a good explanation why is this, but these are the results. And these are true for all the technologies. Okay, so since we see more IO threads gives a better performance in terms of IOPS, let's see what is the cost of this. This is the CPU time consumed by the storage stack. And we can see, as expected, the CPU time consumed scales almost linearly with the number of threads. So four threads, 4 IO threads consume 4 times the CPU of one IO thread. 8 is a little bit less, probably because we just couldn't load it enough from the virtual machine. But the IOPS does not scale the same at the same speed. So the efficiency, how much CPU time is needed to process 1,000 IOPS, is this. The efficiency gets worse by increasing the number of threads. So unless you have virtual machines that really need many thousands of IOPS on a single device, hundreds of thousands of IOPS on a single virtual device, there is no real reason to use more than one IO thread. However, this could be a solution if you are ready to spend several CPU cores just processing IO operations. Okay, the next thing, let me see how's the time. Great. The next is comparing different emulated storage devices in the virtual machine, VirtIO block and VirtIO SCSI. So again, first is the latency. The latency is the parameter that has the biggest impact on the actual applications. That's why we always started with the latency here. So as you can see here, there is some difference, but not so big. For IOUring, there is almost no difference. For native, a virtual block is a little bit better than virtual SCSI, especially for read operations. For the maximum number of IOPS, virtual block can achieve more IOPS on a virtual device compared to virtual SCSI. And the difference is significant, especially for IOUring, but even for native, it's about maybe 30% more than, or 40% more than virtual SCSI. And so this diagram shows the same results, lower maximum IOPS for virtual SCSI and about the same latency for low traffic. For pgbench, results are very close, except for very high load here, where we are very close to the saturation of the system. So when you run at the conditions that you normally will run your system, that is in this region here, there is no significant difference between the two technologies. Although IOPS tests showed a significant difference. Huge pages. So huge pages is a technology of Linux kernel, how it manages virtual memory. It's not related to the block size or anything else. So we compare, in general, physical servers with a lot of physical RAM would benefit from huge pages. However, in this test, huge pages doesn't show significant improvement neither in the latency, so we see some of the results are better, some are worse, neither in maximum number of IOPS that can be processed. Okay, so that was the last slide with the data. So let's see what was the important information that we can extract from this. First, we need to understand the limitation of different technologies. Virtual block has a better performance, but it has some limitation on the old virtual machines. Every virtual block device is a separate PCI device, and there is a limited number of virtual PCI devices that you can have. So you have a maximum number of 28 disks. So not a very important limitation, but the more important is it does not support SCSI commands. If you have some rare application that requires SCSI commands, then you need to use virtual SCSI instead of virtual block. And also guarantee that the whole storage stack supports this. So it's not only on this point. IOUring, where it seems better at some tests, and while it's already 6 or 7 years old, this technology still has some stability issues. Actually, on my tests, 8 out of 10 times the virtual machine with IOUring crashes. So it might be only with this specific kernel, but it was really not something that I would use in production. So if you use IOUring, please make sure you test it very well and in exactly configuration that we will use in production to make sure it is okay. So yeah, this is something that you don't really want to see on your hypervisor. Oops, sorry. Yeah. So from practical point of view, native and IOUring give exactly the same performance, especially if you are not measuring just number, if you run application. Always enable, if you can, enable iothread. It will improve performance a lot because of the lower latency. It will reduce the CPU usage. So always, and it solves many other problems. So always use iothread if possible. Threads is much smaller compared to the other two, but you might not see this in real world application. However, threads consumes a lot of CPU. So this is a good reason not to use threads. VirtualBlock is better than virtuoscasi at high loads. So we're talking about more than 100,000 IOPS. Lower than this, you may not see big difference. Huge pages, at least in my tests, I couldn't find any significant difference. However, applications that use a lot of memory-intensive workloads and other workloads that use a lot of CPU, they might benefit from huge pages. So test this with your workload. Linux native asynchronous I/O, although by design it's asynchronous, in some cases it might become synchronous and it can block operations. So running it in the main QEMU emulator thread means that the whole virtual machine will stall until the operation completes. So this is one of the most important reason to use iothread with native I/O to ensure smooth operation, even if the I/O operation is blocked for some reason. We talk about stability of I/O ring. So all these tests apply in the storage stack that I showed at the beginning, where the QEMU process talks directly to a Linux block device on the host. If you're running different type of storage that runs in the user space, not I/O operations processed by the kernel, like libiscsi or librbd, so Ceph storage, NBD devices, libnvme, again implemented in the user space. So they use completely different storage path. And the result might be very different from what you saw today. So because of this, this also applies for file-based storage, like any storage that use QCOW, image formats, NFS, and so on. So always test your system in the configuration that you use. Do not directly copy the results from here to your project and rely on this. So if it matches to this, okay, it's a good baseline to start with, but so, and I managed to get to the end on time and have 3 more minutes for questions.